Greetings and welcome to Astronomy 104 at HACC. Last time we discussed the basic properties of the stars, and we talked a little bit about the HR diagram, or the Hertzsprung-Russell diagram. For today's lecture, we're going to go into the HR diagram in a lot more detail and talk about that and learn about creating the HR diagram. And what we're going to study here is okay, there we go. We're going to talk about the different components of the HR diagram and how we can create one. Now, HR diagram is a graph. So it's a graph, and it's going to have, therefore, two different axes. So we can look at the horizontal axis and the vertical axis. Now, the first thing we're going to look at is the horizontal axis. So as I said, it's a graph. And we're going to look at what can be plotted on the horizontal axis. And there are a couple different things. We can plot on the horizontal axis, we are measuring the temperature of the star. So it is some way of measuring the temperature. Now we have a couple different ways we can plot that. But all three of these that I'm going to mention that we use are different ways of measuring the temperature. Some are just easier to measure in one way or another, depending on the stars we actually have. Now, if we're doing a theoretical HR diagram, we can actually plot the temperature directly. So directly plot the temperature. And that we can plot exactly. Now, temperature is not, as we talked about last time, temperature is one of the measures of a star that we can get relatively easily. It's actually something we can determine, but it's not an intrinsic property that is measured directly. We can't get a direct measurement of the star just by looking at the star. We can't take its temperature. The things we can get that are related, and again, we talked about these last time. We talked about the spectral classes, the O, B, A, F, G, K, M sequence, so we could plot those on the horizontal axis. Again, from right to left. Plotting from right to left, right would be the coolest stars, and left would be the hottest stars. So I have it plotted right to left, meaning it's backwards from what you're normally wanting to doing. Now, yes, astronomers love to do things backwards. So when we're looking at it, the highest temperatures are going to be on the left-hand side, the biggest numbers, and the coolest temperatures are going to be on the right-hand side. So numerically, the temperature actually decreases as you go along the x-axis, backwards from what we normally do in graphing. But that is the way the HR diagram works. With spectral classes, we can go from the O stars, the very hottest stars, would be on the left-hand side, and then down B, A, F, G, K to M, the coolest main stars, on the right-hand side. So we would plot them again. You're going to plot everything, again, as temperature is increasing as you go towards the left. The other thing that we can plot beyond the spectral class is what we call the color index of the star. The color index is just a numerical value given to the star, and what we do is we look at the star at two different frequencies. And if we talk about that a little bit more here, as we go to the next slide, and we go to the next slide and take a look at that, what exactly is the color index? The color index is the brightness of the star measured in two different filters. So we actually look at two different wavelengths of light, and we measure how bright the star appears to be in each of them. Now, that there's a number of different filters that are used, and there can be different ones, but the standard ones that we use are we look at the star in blue light, and we look at the star in what we call visual light, a yellowish-green filter. So the B and the V filters are the two that we use. And we take the magnitude we measure how bright it is in the B filter, how bright it is in the V filter, and we determine our magnitudes. Now remember, we talked about the magnitudes last time. Okay. So we were talking about the magnitudes in two different filters to determine the color index. And what we use is the magnitude. We determine the brightness, how much light we see coming through each of those two filters. So we take a picture in one filter, we take a picture in the other filter. And when we subtract those two magnitudes, we get what we call B minus V, or the color index. And that's how we define it. It's the blue magnitude, that number we get, minus the visual magnitude, the V magnitude. If we get a positive value for that, that means we have a redder star. And a negative index means we have a bluer star. So two different options there, depending on what happens. If the star is very, very bright in the blue as compared to the visual, then the blue is going to be a smaller number. Remember, magnitudes are backwards. Not only is our x-axis backwards, but our magnitudes are backwards. So if we get a very hot star, if we look at an example, a hot star is going to have a small b because it has lots of blue light, and it will have a large V because it has less visual light by comparison. So if we have a small number minus a large number, we're going to get a negative index, and that tells us that it's a bluer star or a hotter star. Conversely, if we look at a cool star, we would have then a large value for B, meaning less blue light, and a small value for V, meaning more visual light relatively. So we're going to be taking a large number minus a small number and get a positive index for that star. So again, we get the option of getting the way we calculate it. And again, it can be confusing. We'll go through some more examples of this in class. But what we're actually going to get is that the larger the color index, the redder the star is what we find out. Now, so we've determined one axis. Now let's look at the next axis. On the vertical axis, on the horizontal axis, we're measuring temperature. On the vertical axis, we're measuring brightness. And again, we can use a couple different things here. There's a couple different things we can plot. But anyway, we're looking at the brightness. We can look at luminosity. Now, we talked about luminosity and what the luminosity of a star was and what the luminosity of the sun was. And it was simply how much energy the sun is putting out every single second. It's just a measure of how much energy the sun is really putting out. And the other way we measure that in terms of magnitudes is we measure the absolute magnitude. And this is the true intrinsic magnitude. This truly tells us about the star. As compared to the apparent magnitude, which does not. The apparent magnitude is simply how bright the star appears to be from the Earth. In which case the apparent magnitude of the sun is very, very small, meaning the sun is very, very bright. It's negative 26.7. So the sun is extremely bright, apparently, but what is the absolute magnitude of the sun? The absolute magnitude is how bright it would appear to be at a constant distance. So at a distance of 10 parsecs, how bright would the sun appear to be? And it would have a magnitude of about +4. It would be a very, very faint star in the sky, even if it were only 10 parsecs away. Extremely, relatively faint. It would be visible. If you got a reasonably dark sight, it wouldn't be that visible from a very bright city such as Harrisburg. So even then, the sun would not be visible. So we can use those two things. We can use the luminosity or the absolute magnitudes. Those are true measures of the intrinsic brightness of the star. And I also note on here, in special cases, you can use the apparent magnitude. You can use the apparent magnitude when you're looking at a cluster of stars. Why can we do it when we look at a cluster of stars? How come we can use it in a cluster, but we can't just use it in general? Because when we're looking at a cluster, we know that all of those stars are essentially at the same distance from the Earth. So we know we may not, even if we don't know how far away they are, we know that they're all the same distance away. so that their apparent magnitude and their absolute magnitudes are related to each other. If we were just to look at a random set of stars and plot them on an HR diagram, it would have no meaning if we use their apparent magnitudes, because some of those stars might be very close to us and therefore look a lot brighter than they really are, and some of them may be very, very far away, and they might be really bright stars, but they're so far away that their apparent magnitude is much lower. So when we use apparent magnitude, we don't know anything about the true information of the star. When we look at a cluster, we can do that. So when we plot an HR diagram, for most of the things that we plot, we want to look at the apparent magnitude. We want to look at the absolute magnitudes of the stars. Now, let's look at what we can do with an HR diagram here. If we draw our little graph, and we plot on the x-axis, so just to give you a little bit of an idea here, again, we're plotting temperature on the x-axis, and again, it increases moving towards the left-hand side. And then we're plotting luminosity on the y-axis. And luminosity increases going upwards. That one makes a little bit more sense, but remember, when it comes to plotting magnitudes, it still means we're going to be putting the smaller luminosities on the bottom. Okay, so we're going to be putting the smaller luminosities are going to be on the bottom, but those are going to be the big numbers numerically. Now, what can we plot on the axis? We can plot on the axis, on the x-axis, we can plot the spectral types. So we can plot O, B, A, F, G, K, and M stars. So we can plot those stars. That's one way of plotting them. Or we can plot the color index. We can plot B minus V. And B minus V increases towards the right. So we have to watch, numerically. We have to watch and keep in mind what we're actually doing. We have to remember that very, very small B minus V's that are negative color index, means that you have a very hot star. So the negative numbers go to the left. The positive numbers go to the right. So that one makes sense as in terms of how we normally plot something. The temperature is backwards. So we're plotting the hot temperatures on the left and the cold temperatures on the right. Normally we think of it the other way around. You'd think temperatures would increase as you go. Now we have luminosity on the y-axis, and we also have the absolute magnitude. So we can plot the absolute magnitude, exactly how intrinsically bright this really is. Now the numbers will increase. The brightest stars will be at the top. So the smallest absolute magnitudes, negative ones, will be at the top. So we'll have negative absolute magnitudes will be up high, and positive absolute magnitudes will be down low. So those are the different things we can plot. What we need to find out is what happens when we actually plot these. And we're going to see a couple examples coming up. But just to start here, when we plot the stars and we use their absolute magnitude and their spectral class, we get a line of stars going diagonally across the diagram, going from the upper left to the lower right. And we call this is where most of the stars fall, and we call it the main sequence. That is where most of the stars fall. And that is where our sun would be right now. Our sun would be, it's a G star, our sun would be located somewhere right along there on the main sequence. So it's right on the main sequence. Most of the stars that we look at, most of the stars are on the main sequence, and they spend most of their lives there. What else do we find? We're also going to find down below the main sequence. We'll find some stars here. And these are down to the lower left-hand side of the main sequence. They're all below the main sequence, meaning that if you look compared to the main sequence stars, they're hotter and they're fainter. And these are what we call the white dwarfs. So they're very, very hot stars, hence the name white for their color, And they are very, very small stars. They're dwarf stars. Now, the main sequence stars are also normally called dwarf stars, but they are not near as small, and we will talk about the white dwarfs in great detail when we talk about the evolution of stars like the Sun. So we have the main sequence, we have the white dwarfs, and then up above that, up above the main sequence, we have the giants. This is what we call the giant branch. And that is where the larger stars occur. They tend to be very red for the most part and very bright. So we have to think about that. These are very, very cool stars. So they're stars like the Sun or even cooler, but they're many, many times brighter than the Sun. How could that be the case? How can we have a very cool star be very, very bright? We talked about the Stefan-Boltzmann law and how brightness was proportional to depended on the fourth power of the temperature. So what happens here is that, what's the name of these? These are giant stars. So these are much, much bigger than the main sequence stars. So even though they're cooler, they're so much bigger, so much more surface area that they give off so much more light. And then up above that would be what we call the supergiants. You can guess what that means. Those are even bigger. Those are even bigger stars. Much, much larger comparatively than the giants. So we see all these different things. Now, as we go through and talk about the HR diagrams, we're going to look at a couple examples here coming up. And we see that there are, now you can see that as I sketched out, we have the same kind of thing. And this is a plot of temperature. So going from 10,000 to 3,000 degrees. And luminosity as compared to the Sun. So going from 1/10,000th the brightness of the Sun to 10,000 times brighter than the Sun. A tremendous range. And you see that we have the main sequence, again, going from upper left to lower right. Sun's right there in the middle of it. And then we have the red giant stars going up to the upper right side. And we see that they are much, much bigger stars. Now, when we look overall, and we look at the next diagram, again, another example. Main sequence going from upper left to lower right. And then we see the giants. And there's actually several different classes, bright giants and supergiants, as you get up bigger and bigger. You're getting bigger and bigger stars, and then, of course, the white dwarfs down here. So we see the same kind of regions that we've looked at in the previous graph. Now, what else can we learn about the star? We talked about the temperature. We talked about the luminosity. That's how we plot it. Now, how can we learn? We can also learn something about the size of a star from the HR diagram. And we talked about that a little bit when we said we had the main sequence, or dwarf stars. And then we had the white dwarfs. And we had giants. Well, what happens is that diagonally across the HR diagram, we get a line of what we call a line of constant radius. So stars falling along this line, wherever they are, would be about the size of the Sun. Stars lying up above a little bit, across, would be about 10 times the size of the Sun. Up higher, 100 times the size of the Sun, and increasing as we go up. And going down below, we can get stars that are a tenth the size of the Sun. So again, diagonally across, from upper left to lower right, are what we'd call a line of a constant radius. So the further up to the right you go in the HR diagram, the size increases. So size is increasing as we move up this way. So that tells us something about the size of the star, and we can also learn something about the masses. We find that the stars, especially on the main sequence, we'll find that the red dwarfs, the very, very small stars, have much, much less mass than the Sun. And the very, very hot stars, the O and B stars, have many times more the mass of the Sun. So it tells us something about the mass and the diameter of the star. Now, we talked about earlier why we could use apparent magnitudes when we look at a star cluster. If we look at HR diagrams of a star cluster, I said normally we had to use absolute magnitude. So normally that's what we have to use. But when we do a cluster, we can do it. Why can we use the apparent magnitude when we're looking at a cluster? This is a good thing. Apparent magnitudes are very, very easy to measure. It's very easy to go out and take a measurement and say, here's how bright the star appears to be. It doesn't involve any other work. It doesn't involve any other knowledge. It's something that anyone can go out there with the proper instruments and measure that star and say, here's how much light is coming from it. This is the apparent magnitude. Absolute magnitude requires more work because that is intrinsically how bright it is. We can't go move those stars around to a fixed distance to say, here's how bright they should be at this distance. We have to know more about them. But when we come to a cluster, we can use the apparent magnitude because the distances are the same. They are all at the same distance. Not exactly, yes, some of them are a little closer, some of them are a little farther away. But if you're talking about a cluster that has a certain size, that size of that cluster is much, much smaller than the distance between the two. So you could think about it the same way, is that the distance from Harrisburg to, say, London is some amount. And yes, there's part of London that's a little bit closer to us, and there's part of London that's a little bit further away. But overall, that little bit of difference, the size of London, really doesn't make much difference in terms of how far you have to travel just to get to London. Does it really matter whether you're going to the nearer part or to the further part of it? The distance between the different parts really doesn't make any difference. So we can actually use this. We can use the fact that there is a relationship between the apparent and the absolute magnitude, and we can calculate the distance to the cluster. That's a great thing. Distances are hard to get. It is very difficult to determine distances in astronomy, and we've started talking about this. We talked about it a little bit earlier in the class, and we will continue this. Distances are one of the key things. We want to learn distances to different objects, but it's not something that's just a simple, easy thing to get. It takes some work. And what we have to do is, we can measure. So we can measure the magnitudes and we can determine the distance. If we can get, say, the apparent magnitude, which is small m, in our equation here, this is apparent, we can measure that. And if we know the absolute magnitude, there's the key, we have to know this for those specific stars. We can look at that, if we can figure out that, if we know that number. Again, that's a hard one. We do have to figure out how to get that. That's a little bit harder. But if we can measure the apparent, that's easy, and we can get the absolute, then we can solve this little equation and we can get the distance. So we can immediately get the distance to this cluster. Again, something very, very important. How do we get the absolute magnitudes? What we can do is once we've determined the main sequence, we can determine where the star falls on it. So if we determine a spectral class for a star, so if we measure what its spectral type is, and we determine, for example, that it's on the main sequence, then we can tell how bright it should be. So if we say we have a G2 star on the main sequence, that would be a star like the Sun, we can say that we know its absolute apparent magnitude would be about 4. So we know its absolute magnitude. If we then measure its apparent magnitude, the difference between those two, and we can solve the equation, we can determine the distance. And that's a method we call spectroscopic parallax. And as long as we have a star where we can actually measure a spectrum, as long as we get enough starlight that we can separate that star and measure the spectrum to determine its spectral class, we can get a distance to it. So it's our next step on the distance ladder. We talked about parallax earlier by measuring the angles. That was a direct method. By measuring that, we got the exact distance to the star. The problem was we could only do it for a few stars. It didn't work for everything, because that angle got very, 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 very small very quickly. So it only worked for the closest stars. This extends our distance scale out a little bit further, because now as long as we can see the star, we can get a distance to it. So it's a big help in determining our distances. Now here's some examples of what we might get. And if we look here, we have, again, our main sequence. And we find that when we look at a cluster, there's a point where the stars are turning off the main sequence and heading to the red giants. This turn-off point, that we call it, tells us the age of the cluster. Because the stars, the hot stars, the O, B, A, F stars, age very quickly. They go quickly through their lives, and they move off to the giant branch. So as we go through the life of this cluster, the main sequence would have been up here at one point, and now all those stars are dead and gone. And these stars here, like the sun, are still on the main sequence, but the other ones here are just ending their life and are just turning off and be going into the red giant phase. And you'll also see a great number of white dwarfs if you look at a cluster like this, because lots of stars have ended their lives, and this white dwarf is the end state for a star like the sun, and even for somewhat bigger stars. So they're all down here. So that turn-off point tells us about the age of the clusters. So we can also, not only are we learning distances, but we can learn ages. This is a great way to study what we call stellar evolution using the HR diagram. And what it is we can learn about the life cycles of the stars by studying the HR diagrams of different clusters. The cluster on the right, you see the turn-off, there's all the stars on the main sequence, and there's some red giants, a few, but the stars are turning off much, much hotter. It's the B stars, maybe, that are turning off. So this is a younger cluster. So this would be a very, very old cluster, and this would be a very, very young cluster. So we see differences in the age. We can learn about the ages of the clusters. We learn about the distances to the clusters. It's a very good way of learning about the stars. It's one of our ways of studying the stars. Now, what can we learn from the HR diagram? We talked about stellar evolution. We talked about the lives of the stars and what we can learn about them. And what we learn is that over its lifetime, and we can't observe this. We do not actually see this happening. We can infer it from looking at, for example, star clusters. But a star moves around in the HR diagram over its life. We can't observe it because even for the fastest moving stars, it's so slow compared to our lifetimes. It takes it such a long time to move. The sun will stay on the main sequence for 10 billion years. It's been there for 5 billion years. It'll stay there for 5 billion more. We can't actually watch it move. We get to infer it by looking at star clusters. We can say, here's what happens to these stars as they go through their lives, and we can use that to perfect our models of how the stars work and how they will evolve and how they will change and become giant stars, how something like the sun will become a giant star. Now, when we look at this, the sun, if we draw our main sequence again here, the stars are actually born here, way off to the upper right. Very, very big stars, very, very cool stars. Off beyond, or even beyond the red giants. And they move downward and finally move to the main sequence as they actually begin to burn hydrogen. Now, we don't normally see this. This is normally hidden in gas and dust. So they're hidden in gas and dust clouds. So we don't actually watch the formation. Remember, we've talked about that in some ways, and we'll come back to it again in the next section when we talk about the formation of stars in detail. But it's all hidden. So all the formation is hidden. It's buried into these deep, dark dust clouds, and we can't see them. Or can we? We actually now can use things like infrared and radio to look into the stellar nursery and peer in there and see what's going on. But the stars are born, and they slowly move down this main sequence. Again, all we're going to see is a snapshot. We see how that cluster is, or how those stars are at this instant. If we could come back millions of years later, billion years later, we could actually see that they've moved. But in our lifetime, we're not going to see it. So the stars move to the main sequence, and they live there. How long they live can range from a few million years to 100 billion years, depending on the size of the star. The very biggest stars may last 1 million years on the main sequence. Very, very short time when you consider the sun will spend 10 billion years, and some of the very faintest stars could last 100 billion years on the main sequence. Once it does use up its fuel, they go back towards the upper right. So back to where they were born, forming a red giant or a red supergiant. And we may go through this multiple times. And again, we'll go through much more detail in this later on. And then eventually, stars like the sun will end up going around and following on the white dwarf part of the sequence. So in the lower left-hand corner, they'll form there. It'll be just a dead core, and it will slowly cool off. There's no other major changes after that except for it just cooling off as it goes through its life. Now here's an example of that again. So you saw my sketch there. Now here's an actual picture of it. Again, the main sequence, and this is showing the later stages. But it starts here at number 7 on the main sequence. As it exhausts its hydrogen, it moves upward. It's getting bigger and bigger and bigger. It finds a new energy source here and comes to rest on what we call the horizontal branch as a red giant. And then it moves, when it uses its fuel again, it moves up again. And then it goes very, very quickly through the planetary nebula phase and down to the white dwarf. Planetary nebula phase is very, very quick. It might last 10,000 years. I know, that sounds like a long time, but again, remember the time frames we're talking about. For a star like the sun, 10 billion years on the main sequence. Then time is a red giant. It goes through the planetary nebula phase, and we'll look at a picture of one of those here in just a minute. After it goes through that, it spends only 10,000 years there. It's a tiny, tiny fraction of its life. So when we see planetary nebula out there, we're seeing a very quick snapshot of the death of a star. Now look at stellar evolution and how stars evolve. And again, we're going to come back to this again later on. So we're just kind of summarizing right now. And what we see is that the massive stars evolve faster. And I've sort of been talking about this already. Stars like the sun might take 10 billion years on the main sequence. So we're barely going to see them budge. Very, very massive stars might take 1 million years. We're still never going to see them budge. They're still much longer lives than we can, as humans, can actually envision. But much, much faster star-wise. 1 million years versus 10 billion years. A big, big difference in how long they do. And lower mass stars than the sun could last 100 billion years or longer. So depending on the mass, the stars evolve faster and slower. And that's what we saw when we looked at that turn-off point section. Remember, we talked about the turn-off points. And that told us that the more massive the star, the higher up it is on the main sequence, the faster it evolves. The lower down on the main sequence, it's still sitting there on the main sequence. All those big massive stars are long dead, but here's some that are still going. Stars like the sun end up as a white dwarf. So they will actually end up as a white dwarf and down in towards the lower section. What is a white dwarf? Go back here again. Again, we looked at this graph. And we see that we go through there and we end up down on the white dwarf down to the lower left-hand side here. Now, what is a white dwarf? Very, very hot, extremely hot. Hot as some of the hottest stars or more. Very, very tiny. These things are the size of the Earth. Right about the size of the Earth, but they're the mass of the sun. Therefore, even though they're very, very hot, Hot would make them very bright, but they're so tiny in comparison that they're very faint. So they're hard to detect. Very, very faint because of their small size. They're in the lower left corner of the HR diagram, and they slowly go they slowly move from where they are down towards the lower right as they cool off. And this is the dead core of a star. So this is what happens at the end of a star's life. It's what the core of the sun will be like 6 billion years from now. And here's an example of a planetary nebula. You have the white dwarf at the center, noted here by the arrow, and you have the outer layers that have expanded out into space. So you can think of it as a gigantic star. At one point this was a red giant or red supergiant, and then eventually those outer layers just got cut free. They were moving too fast and they were too far out that the star could no longer gravitationally hold them, and they have just expanded out into space. If we come back to this planetary nebula 10,000 years from now, it'll be gone. Eventually the white dwarf will no longer be hot enough to heat up the material, so it will fade in color and fade to darkness, and it will slowly expand out into space, completing the life cycle of the stars, because it can then be used to form new stars. Finally, to conclude, the HR diagram is the key diagram in stellar astronomy. To study the stars, it is what we need to use. It tells us about the temperature of the stars, the brightnesses of the stars, the mass, the radius. We can put stars on there, we can see what happens, what would happen to them. We can study how stars evolve. How would their temperature and luminosity change over time? Most of the time is spent on the main sequence. That is where the star lives for 90% of its life. It's spent on the main sequence. It spends then a little bit of time as a red giant. It spent some time as a protostar. That's what's coming up next. And it'll finally end its life as a white dwarf. And it will stay there forever. It'll be a white dwarf, then it'll become a black dwarf once it cools off. So, hope that has helped. We've gone over a little bit more on the HR diagram. Again, we studied this a little bit in the last chapter, but it's such an important thing that I wanted to spend one whole lecture just going over the HR diagram and giving you some ideas. And we will come back to this. When we talk about stellar evolution, we're going to talk about star formation in the interstellar medium next time, and then we'll talk about the evolution of stars, and we'll go through all that, and we will constantly be using the HR diagram. So, have a great day, everybody. That finishes this lecture, and I will see you in class.